Hello, this is Dr. P. Kadirvel, Professor in Civil Engineering, Kamaraj College of Engineering and Technology, Madurai. This video presentation 3D CAD using STAADPro is about modeling, analysis and design of a 3D RC frame using STAADPro software. STAADPro is one of the most popular structural analysis and design software which is supplied by Bentley. In this presentation, we will be seeing the modeling of the 3D frame for gravity load, which includes dead load and live load, and design based on IS 456 2000. This video presentation is for academic purpose only for all the civil engineering student community. The outline of the presentation is as follows: introduction followed by structural analysis, structural design, CAD, which is computer aided analysis and design, CAD modeling inputs, gravity load, which includes dead load and live load on the structure, types of structures, and then the exercise on 3D space frame with RCC. Structural analysis is the process of finding the unknown internal forces due to the external load applied. The external loads are mainly due to dead load, which includes the self-weight, floor finish, permanent loads, etc. as specified by IS 875 Part 1, and then live load, which includes the people, furniture, imposed load, etc. as mentioned in IS 875 Part 2. So both these dead load and live load includes the gravity loads, which acts vertically downwards. And then there is possibility of wind load as per IS 875 Part 3, seismic load as per IS 1893 2002, and IS 13920, the ductile detailing code. In addition, the various other loads includes the snow load, construction loads, etc. So due to the external loads which are applied on the structure, internal forces gets developed in the structure. Finding out these forces is known as structural analysis. So generally the types of internal forces are bending moment, shear force, axial force, and torsional moment. Beams are flexural members which are subjected to bending moment, shear force, and torsional moments. Slabs are similar to beams which are also subjected to bending, shear, and torsion if any, where the breadth of the member is taken as 1 meters for design. And then columns are vertical members subjected to mainly axial compression. In addition, moment along X and Y if any. And footings are also designed for axial compression along with moment along X and Y if any. Structural analysis is followed by structural design, where suitable section areas are arrived based on the internal forces developed. In RCC, the sufficient area of concrete and steel are arrived to take care of the internal forces developed. For RCC, the limit state method is generally adopted for design based on IS 456 2000, and in structural steel design, both working stress method and limit state method are available based on IS 800, and the code of practice for working stress method is 1984, and limit state method is IS 800 2007. CAAD stands for Computer Aided Analysis and Design. The three stages in this CAD for any software includes pre-processing, processing, and post-processing. The pre-processing stage includes the modeling or input, in which the dimension, which is the length of the member, the cross section is fed into the system. So from this cross section, the moment of inertia is arrived, and along with that the material is specified, from which the Young's modulus E is taken as input. So these two parameters are important for analysis, E and I, which are required to find the internal forces by analysis. And then support conditions are given, either fixed, hinged, or simply supported, and finally the loading on the members. So these all put together form the input or the modeling stage, which is the pre-processing stage. The second step is the processing, which is done by the software, mostly by matrix method, and here STAAD does it by stiffness matrix method. The third stage is the post processing, where after the processing is completed, the output can be viewed as tables and diagrams from which the internal forces can be visualized as diagrams and tables. Both the results can be viewed in diagrams and in tabular form. The internal forces of bending moment, shear, axial force can be viewed, the stresses can be viewed, and the deflection can also be seen. So while elaborately seeing the CAD modeling inputs, which is the pre-processing stage, the first step includes the dimension where the length of the members are given, nodes are given as input, and members are drawn between the nodes to get the length. The second step is giving the cross section, where while the dimensions of the cross section are given, the software finds the moment of inertia, which is the geometric property. So for rectangle it is PDQ by 12, and for circle it is pi d power 4 by 64. The third stage is giving the material as input, from which the Young's modulus is taken inside. So generally for RCC it is 5000 root FCK based on the characteristic compressive strength of concrete, and for steel it is 2 into 10 power 5 Newton per mm square. The fourth step is to give the support condition. Generally the three options available are simply supported, the example being slab resting on walls, and hinged, the example being bolted connection, and fixed, where the beam reinforcement are developed into the columns. And then the fifth stage is loading, where member loads can be given as uniformly distributed loads, uniformly varying loads, concentrated loads, floor loads, etc. And joint loads, which are the nodal loads, given as wind load and seismic loads. Gravity load includes the dead load and live load on a building or any structure. In this, dead load calculation is based on IS 875 part 1, where the load includes the self weight of the member, floor finishes, other loads like partitions or fillings, brickwork load if any, and any other permanent loads. Looking into the dead load, generally the load is found on the slab and the beam. While finding the load on the slab, the load is given as area load in kilonewton per meter square. The load on slab includes self weight of the slab, floor finish, and other loads like partition and filling. Self weight of the slab is found by multiplying the thickness into its unit weight, which is generally taken as 25 kN per meter cube for RCC. An example is shown for a 5 inches slab of 125 mm thickness, which is 0.125 meters. The self weight is 0.125 into 25, which comes to 3.125 kN per meter square. The second is the floor finish, which may include cement flooring, tiles, marble, granite, etc., which accounts to 0.6 to 1 kN per meter square, except for the roof finish, where weathering course with tiles are provided. The loading can be taken as 2.5 kN per meter square, and other loads, if any, including the partition or sunken slab, is arrived based on the actual loading. The sum of the three loads gives the total load on slab, which is the area load in kilonewton per meter square. The load on beam is taken as UDL, which includes the self weight of the beam, the brickwork load if any on it, and then the load from slab either on one side or on both sides. The self weight of the beam is arrived by multiplying the cross sectional area into the unit weight, and brickwork load if any is arrived by multiplying thickness into height into unit weight of brick, and then load from slab is arrived by multiplying the area load into the area contribution, either it may be triangular or trapezoidal based on the yield lines, by which the load is converted into UDL on the beam. So summing up all these three, you get the load on the beam as UDL. Examples have been shown for self-weight of beam, brickwork load, and load from slab. From this, the dead load on slab and beam are calculated, which are to be fed into the software. The live load is arrived based on IS 875 Part 2, where Table 1 of IS 875 Part 2 gives the occupancy classification and the loading for each category. The loads are given as area loads in Table 1, which are the loads to be applied on the slab. For example, the rooms in residential building 2 kN per meter square load is taken, and for assembly buildings with fixed seats 4 kN per meter square is taken. Similarly, for various types of buildings with various occupancy, the loads are listed in Table 1. This area load on the slabs are converted into uniformly distributed load on beams by multiplying the slab load with the area contribution of the load in the slab. Thus, the area load on the slab is converted into distributed triangular or trapezoidal loads on the beam. So to begin with a new exercise in STAADPro, initially the type of structure need to be selected. So basically there are four types which have to be given as input. The first type is space, which is a three-dimensional framed structure with loads applied in any plane. The second one is plane, which is bound by the x and y axis. The examples are for continuous beam and 2D frames. The third one is floor, which is two or three dimensional having no horizontal movement, which is generally in the x and z axis. The example being floor slabs, grid floor, and raft. And the fourth type is the truss, which consists of truss members which can have only axial member forces, which are either tension or compression, and no bending or shear is allowed when type 4 trusses are selected. So strictly trusses, only the fourth option need to be selected. And then the units default, generally it is given as meters for length and kilonewton for force. We shall now begin with the exercise of 3D space frame in RCC. The structure selected is a G+2 residential building. The number of bays in the x-axis, which is along the length, is 4, of length 3 meters, 5 meters, 4 meters and 2 meters. The number of bays along the z-axis is 2, which is the width of the building, with bay width 4 meters and 5 meters. The number of bays along the y-axis, which is the height, is 4, which includes the foundation, ground floor, first floor and second floor. The bay heights are foundation 2 meters, ground floor 4 meters, first floor 3 meter and second floor 3 meters. The dimensions are shown in the isometric view of the structure, and the three-dimensional rendered view of the frame is also shown. This slide shows the views of the structure in the top, side and front directions, also in the isometric view. So all the dimension of the members is visible here. The top view shows 4 bays in the front side and only 2 bays in the back side. The modeling in the software can be done by any means. Here we shall discuss 3 methods of giving input the dimension of the members. In the pre-processing, the first step deals with input of the dimensions of the members, which includes the beams and the columns. We shall see the method 1, by which nodes and beam elements are added. They are copied in all the 3 axes. In method 1, first step, to add the nodes, go to geometry menu. Under that nodes, you have to enter the XYZ coordinates of the 5 nodes as shown in the slide. First node is taken as the origin 0, 0, 0, second node 3, 0, 0, third one 800, fourth one 1200, fifth one 1400. The 5 nodes, the coordinates are entered inside. So these are the first line of nodes in the bottom along the x direction. Now using the node cursor, select all the 5 nodes, right click, select copy, once again right click, select paste nodes. It asks for the coordinates either in the x, y or z axis. Under the z axis, enter the distance -5 meters. Click OK. The second set of 5 nodes appears on the screen. Now repeat the previous process once again by pasting the nodes along the z-axis at a distance of -9 meters. The third line of nodes appears on the screen. So all the 15 bottom nodes have been given as input inside. Out of the 15 nodes, the top, extreme left and extreme right nodes need to be deleted. Once again select the node cursor, select the 2 nodes, right click, delete. The 2 nodes get deleted. Finally 13 nodes are available. Now select the 13 nodes, right click, copy. Once again right click, paste nodes. Give the distance in the y direction for 2 meters. Click OK. Another set of 30 nodes gets generated along the y-axis. You can now rotate all the nodes by selecting rotate up. You can get a clear view of all the 26 nodes. Now the second step is to add members between the nodes, the columns and the beams. So select geometry menu, under that add beam from point to point. Select the bottom node and the top node along all the lines so that you get 13 vertical members. Similarly, connect all the top nodes so that you get the beams which are actually the earth beams. Now the first level of columns and beams have been generated. Go to the front view. Using the beam cursor, select all the beams and once again go to the isometric view to check whether only the beams have been selected. Now right click, copy, once again right click, paste beams. You get the XYZ coordinates. In the y direction, you give a height of 4 meters. Click OK. You get the next level of beams generated. This is actually the ground floor roof beams. Now once again go to geometry, add beam, and you can connect the column from the earth beam to the ground floor roof beam for all the 13 columns. Now the second level of columns and beams are generated. Repeat the same process for the first floor and the second floor level. Thereby you get the entire structure. This is method 1 of generating the structural model with the dimensions of the beams and columns. The second method of creating the model is by translation. Under geometry, you have an option of translation repeat, by which these copy paste options can be done very easily. So for method 2, the first step is the same, add nodes. Under geometry, you need to create the 5 nodes as done in method 1. Now select the 5 nodes using node cursor, go to geometry, under that translation repeat. You get the dialog box of translation repeat. In that you have to enter the global direction Z and you have totally 2 steps. So number of steps is 2. The first step is 4, second step is 5. Click OK. Now you get totally 15 nodes. As done in the method 1, you have to select the top, extreme left and right nodes using the node cursor. Right click, delete, OK. So here you get the bottom 13 nodes. Now select all the 13 nodes using the node cursor. Go to geometry, translation repeat. In the global direction, select Y, number of steps 1, give the spacing as 2, and here you have to check the link steps. Now click OK. The link steps command is given to connect the columns while the nodes are generated at the top. You can see the 13 columns have been generated. Now the second step, go to geometry, add beam from point to point. You connect all the column top nodes so that the earth beam is generated in the model. Thereby you get the first level of the frame. Now once again select the beams alone by going to front view and selecting all the horizontal lines along the earth beam level. Go to isometric view once again, check whether the selection is right, and now go to geometry, translation repeat. In the global direction select Y, number of steps 3, and give the 3 spacings as 4 3 3, and link steps ticket, click OK. You can see all the other 3 levels are automatically generated here with the columns. Now the dimensions of the structure is complete by method 2. Now coming to method 3, standard library models are available inside STAADPro itself. So here we are going to generate the structure using a standard model. Generally, symmetrical model is generated from which adding elements or deleting elements is done to finally get the required model. Here under geometry menu, select run structure wizard, which is the bottommost option available. A new window opens. Here in the left side model type, select frame model. Under that bay frame, double click it. You get the select parameters option. Now you have to give the entire length, height and width of the model. For us here, length is 14 meters, total height is 12 meters, total width is 9 meters. Of base along the length, height and width are given as 4, 4 and 2. Now each of the bay width along the length, height and width have to be entered through the button with 3 dots available next to the values entered. Now first click the button with the 3 dots along the length row. You can see all the 4 bays are equally split by default. You need to change the length for all the 4 bays as 3, 5, 4 and 2 and click OK. If the total does not sum up to 14, the software will not allow to close the dialog box. Similarly, the length of the bay along the width direction and the height are entered separately. So along the height, the bay lengths are given as 2, 4, 3, 3, and along the width, the two lengths are given as 4 and 5. Click OK. You can now see the 3D model is generated as such. Now go to File and click Transfer Model to STAADPro. Yes and OK. So now you can see the model is transported into the STAADPro software. So here you can see the wizard is used to generate symmetrical frame along the X, Y and Z directions. Any additional member required need to be added, and any members which are not required and available in the model has to be deleted. Now go to the isometric view. Using the beam cursor, select the extreme left column and the beams connected to it by cross window select, you can see the unwanted beams and columns have been selected. Right click, delete, OK. You can see those members have been deleted. Go to the top view and you need to delete the top extreme right columns and the beams connected to it. So using the beam cursor, make a cross select and go to the isometric view and check whether the selection is right. Right click, delete. You can see those members have also been deleted. And once you go to the isometric view, you can see the final frame, which is the required model. So this is method 3 to generate the model with the dimensions. So any one of the above 3 methods shall be adopted to model the frame with the dimensions. The second step in the pre-processing is to give the member property, which are the Young's modulus and moment of inertia. The Young's modulus, capital E, is the material property, and moment of inertia, capital I, is the geometric property. Now first we shall give the dimensions and material for the columns. One important information to be noted is the size of the column given here does not ascertain the safety of the members. The size given here is only to compute the moment of inertia I, by which the internal forces can be arrived. The safety of the member is checked after analysis only. Now to select all the columns, go to the select menu, select beams parallel to Y. All the columns get selected, which you can see in the isometric view. Go to commands menu, member property, prismatic. Prismatic literally means from the start to the end the cross section is the same, and we shall start with a size of 0.23 by 0.23 meters for the column. The default material selected is concrete. Just click assign and close. You can see all the columns have been assigned with a preliminary size of 0.23 by 0.23 meters. Now to get rid of the text RECT 0.23 by 0.23, go to the symbols menu, which is a right triangular toolbar at the top. Under properties tab, select none. OK. So the text alone goes off. The properties have been entered for the column from which the E and I values have been computed by the system. Now repeat the same procedure done for the columns for the beams. Using the beam cursor, go to the select menu, beams parallel to, first select X. Once again go to select beams parallel to, now select Z. All the beams in the X and Z direction gets selected. You can very well see it in the isometric view. Now go to commands, member property, prismatic, rectangle. You can give a preliminary dimension of 0.23 meter breadth and 0.3 meter depth. I once again repeat, these are only preliminary values. They do not ascertain the safety of the members. These are only for analysis purpose. The safety is checked in the last step after analysis. Material by default is concrete. Click assign, close. You can see the member properties have been assigned for all the beams. The text appears in all the members. To get rid of the text, go to symbols and labels, properties, none, OK. The text alone goes away, but the properties have been assigned. To confirm whether the sections of the columns and beams have been assigned, you can go to the rendered view toolbar, which is a dark brown rhombus shaped toolbar which is available in the slide. Once you click it, you can see whether the sections have been assigned for the beams and columns. The orientation of the beams and columns can also be visualized in the rendered view. Now we can close the rendered view if everything is fine. The third step is to give the supports. Go to the front view, select node cursor, select all the bottom nodes, go to Commands menu, Support Specification, Fixed, Assign and Close. You get the bottom nodes as fixed. You can verify whether all the bottom nodes have been assigned fixed support by going to the isometric view. The fourth step is to give the loading. The dead load and live load on the slabs and the beams arrived have to be given as input inside. Now select Commands menu, under that loading, primary load. The default number is 1. Change the name to DL, meaning dead load. Add. Now for number 2, type the name as LL, meaning live load. Add, close. Now two load cases have been added as DL and LL, which is appearing on the right hand side window. Now select DL, the first load case, and click Add in the new window. You get various types of loading listed in the new window left hand side. By default, the first option of self weight is displayed in the direction Y with -1 factor. Just click Add and close. Now select all the members including the beams and columns. Select self weight Y-1 in the right hand side window, and in the right hand side window bottom you have assign to selected beam. Check it and click assign. The self weight of the beams and columns are automatically calculated and assigned, meaning the cross section of the members into unit weight. Now to feed the brickwork load, if any, select DL, click Add, Member Load, Uniform Force. So this is to be given for UDL, and the direction is in the GY, which is global Y axis, and the value you can enter as -14 kN per meter in W1. Click Add and close. Now this load has to be assigned to the beams which are subjected to brickwork load. Here let us assume all the beams including earth beam, ground floor roof beams and the first floor roof beams are subjected to the UDL of -14 kN per meter. Therefore, go to the front view, select all the beams alone using beam cursor. By pressing Ctrl, you can select each level of beams, except the roof beams where only parapet walls may be provided. Now select the UDL load added in the right side window which has not yet been assigned, which can be seen by the red question mark in the load. Select it, click assign to selected beam at the bottom, assign. You can see the UDL being assigned to all the 3 level of beams. Next, the slab load has to be fed in. First, the dead load on the slab. Select DL on the right hand side window, click Add, select floor load. So the area load which has been already computed including the self weight of the slab, floor finish and partition or filling load if any is assigned in the floor load. Here in this example we have computed the dead load as -4.5 kN per meter square. Therefore, enter the pressure value as -4.4 kN per meter square, and next define Y range. Enter the minimum value as 6 meters, maximum value as 12 meters, meaning the level of the ground floor roof where the slab comes in is at 6 meters from the base, and the topmost second floor roof is at a height of 12 meters. All slabs in between these two ranges bounded by beams are assumed to have floor load, and the load gets distributed to the surrounding beams based on yield line theory. So once I click Add and close, you can see the floor load is assigned on the frame, which can be visualized by clicking the Y range load under the DL condition. You can see the yield lines along the 3 levels. So for clear visibility, you can go to the top view, by which you can see the load pattern distribution from the slabs to the beams as triangles and trapeziums. Similarly, the live load on the slabs are also entered as floor loads. Now select LL, which is the second load case on the right side window. Click Add Floor Load. Under pressure, enter -2 kN per meter square. Since it is a residential building, for all rooms, here we assume the live load as 2 kN per meter square. In case the value changes based on the occupancy, the value can be changed. In define Y range, give the minimum as 6 meters, maximum as 12 meters. Click Add and close. To view the load, once again under LL, select Y range. You can see the yield lines in the floors for the 3 levels. To view the yield lines of any single story, go to the front view, select that particular story including the beams and columns, right click and select new view. You can see the yield lines of that level alone can be clearly visible. Once again, to view the entire model, you can click the toolbar having display whole structure as shown in the slide. Now the gravity loads, dead load and live load have been entered inside. Since we are going to do the design by limit state method, the basic load combination of 1.5 DL plus LL need to be added. So to give the load combination, select the new option in the right side window, click load case. Under that, enter load number 3, the name as 1.5 DL plus LL, change the default value to 1.5 and send the left hand side options of available load cases 1 and 2 to the right hand side using the arrows available. Now click Add and close. The third load case is the combination, which is 1.5 DL plus LL and shown in the window with a blue colored symbol C, 1.5 DL plus LL. Now it is here that both the dead load and live load act simultaneously with a factor 1.5. This completes the fourth step of loading. The fifth step in the pre-processing is the analysis command. So go to the commands menu, click analysis, perform analysis print all. So this command is given to analyze the model and to get the results. This should be given only once, even when modifications are done later. The sixth step is the design, where the design parameters are given as input and the members are assigned as beams and columns for design. It is here that the country code need to be selected for the design. As we already know, analysis is universal, but design is dependent on the country code. The two parameters for design of RCC are grade of concrete FCK and grade of steel FY. Initially, the two parameters have to be designed. So select all the members, go to commands, design, concrete design, current code IS456. Once again select all the members, click define parameters in the design window, select FC and enter it as 20,000 kN per meter square, meaning M20 concrete of characteristic compressive strength 20 Newton per mm square. Click assign. Now select FY main, which is the grade of steel for the main bars. Enter 5 lakh, meaning 500,000 kN per meter square or 500 Newton per mm square. Click assign and select FY secondary. These are for the lateral ties and stirrups. Once again give 500,000 kN per meter square. Click assign and close. You can see the green tick mark in the design window for IS 456, the Indian code, FCK, FY main and FI secondary with values. Now deselect by clicking in the screen background. Go to the select menu, select all the columns with members parallel to the y-axis. In the design box, select commands, design column, assign, close. Now once again deselect, then once again go to the select menu, select all the beams by clicking beams parallel to X and Z using the beam cursor. In the design box, click commands, design beam, assign, close, deselect. So it is here that we define all the horizontal members as beams and all the vertical members as columns. They are designed as per IS 456 2000. Finally, to get the quantity of concrete and steel in the beams and columns, select all the members including the beams and columns, go to command box, under that commands, click take off, assign, close. So that completes the sixth step of design. The seventh step, go to the analyze menu, click run analysis, done. So the third once stage the input is correct, CAD is post processing. You can see the processing is done. Post processing from the mode formation menu of the element stiffness matrix, assembling them into the global matrix, can be solving in diagrammatic and finding out the unknown internal forces. The internal forces from analysis can be viewed if there is any error in the input by clicking the stops midway degrees of freedom. FX, FY, the processing, MX, which is the second stage of CAD, is done by from the buttons which are available in the toolbar at the top. MZ shows the bending moment diagram in the frame. FY shows the shear force diagram. Fx shows the axial force diagram. Mx shows the torsional moment, if any. So once you click them, you can see the diagrams as shown in the slide. To view the values of the internal forces developed, go to the result menu at the top, click view values, beam results, and check, that is, put a tick mark in the locations where the values need to be displayed. Here you can tick bending at end and midpoint, shear at end and midpoint, axial at the ends, and displacement to get the maximum resultant values. Now click annotate and OK, click close. Now if you click MZ, you can get the bending moment diagram with the values, and if you click FX, you can get the axial force diagram with the values. The values seem to be congested. You can view the values level by level by going to the front view, select a single level alone with the beams and columns, right click, select new view, OK. You can see that individual level alone is displayed with the bending moment diagram. Now it is clear for visibility. Same way, the shear force and torsional moment, if any, or axial force of each level can be visualized. To see the deflection, you can select the button with the green arc, which shows the deflection of all levels. Here also similarly, you can select each level to view the deflection at various points in the frame. To view the design results of the beams and columns, you can double click on the corresponding member to see the design result under the concrete design tab. For example, in the screen you can see the bottommost column corner of the frame is selected. Double click, you can see the last tab is the concrete design where the diagram of the design result is available. This concrete design tab is available only when the member is safe, or if only the design command for column is given previously. If not, in both the cases, it may not be available. So that example is given in the second screenshot, where a inner bottom column does not show any concrete design tab, meaning it's not safe. The dimension of 0.23 by 0.23 meter was not safe. To make the member safe, The possible options are to increase the cross section of the member, or increase the grade of concrete, or increasing the grade of steel, or the combination of any of the three. So like this, all the columns in every level is checked, and those columns which are not safe, usually from the bottom to the top, those members are selected, and the cross section with the grades can be increased and redesigned until it becomes safe. Similarly, the beams are also double clicked to see the concrete design tab, where the design results are visible with the main reinforcement and the shear reinforcement. Here also, if the member is not safe, the concrete design tab will not be available. To view the design result of a beam or column in between the levels, you can go to the front view, select that level alone, right click, click new view. You can get that level alone. Now you can double click the beam or column to get a better visibility of the design results. So it is once again emphasized, to make the members safe, it depends on the person who designs the model to redesign by changing the dimensions of the members or grade of concrete or grade of steel. The design output can be visualized by clicking the STAAD output button at the top and clicking concrete design in the left hand side. The design summary of each and every column and beam are listed one below the other. Here also the area of steel required with the dimensions are listed for verification. So that completes the exercise of 3D CAD modeling, analysis and design of a space frame with RCC using STAADPro. As already mentioned, this is a preliminary exercise for analysis and design of a 3D RC frame using STAADPro for academic purpose, to enable the student community to begin with 3D modeling in STAADPro for gravity load, including dead load and live load. Thank you.